Good morning, students. So, in the previous video, we had discussed about the free body diagrams, and there what we have done is we have just looked at how to draw the free body diagrams and how to infer the force equations from the free body diagrams. And as a result of this, we have also seen if the body is at rest, if the object is at rest, how to determine it, and then what are the forces acting on when the object is in equilibrium. So towards it, we have taken one example wherein the object was at rest in a horizontal table. Then we had looked at when there was a force applied and the object does not move. Again, the object is in equilibrium. So then how do you discuss this here? Then an extension of the same problem was also seen here, wherein here we had one force which was pulling, and here there are two forces which is pushing, and one force which is in the opposite direction. So this also we discussed. We found out how to write the force equations. And then we also looked at when you have an object which is being strung by two different strings, and then the angle made by these strings with respect to the horizontal is going to be 60 degrees. Then you observe that the tensions are same. And based on this, we found out, okay, how do you resolve these tensions? How do you draw the free body diagrams? How do you arrive at the force equations? This is what we have observed so far. Then the next example. So I said that, okay, if the angle between these two is 60 degrees, which means if it is an isosceles, if it's an equilateral triangle, you'll be able to do this. But what if the angle is not 60, but it is something else? For example, here, if I put this as 45, and here, if I put this as something like 70, okay, and then this is 65 over here, then definitely the tensions would be different. See, this tension T1, this tension T2. So in the previous example, I've assumed the tension here and tension here were one and the same. In this example, I did not assume that, but instead I said the tensions are different. This shows you when can you assign, okay, the tensions are identical or tensions are different. So based on, okay, what are the lengths of the string? See, this length would be different, this length would be different. So based on this, again, we resolved it and finally got an example here, right? We were able to solve it. I gave you 4 options to get the answer. And after that, we also looked at, okay, something like a particle, which is an object which has been sliding along an inclined plane. And in that case, how do you determine, okay, what is the force? Okay, how do you resolve that? And here, the difference here is that you observe that the x-axis is no more horizontal, but instead, we see that the x-axis is made along the plane over here, and the y-axis is perpendicular to the plane here. That's what we had seen. And based on this, we resolved this mg force into 2 components, mg cos 30 along downward direction, and then you see that mg sin 30 along the downward direction here, okay, vertical perpendicular to the plane, and thereby we equated, and hence we got an expression for the acceleration or maybe the normal force. Then, and after that, we looked at why only rectangular objects, why not we take up circular objects or spherical objects. I took a plank, I took up something like this, okay, a triangular wedge, okay, and the angle between these wedges, angle of the wedges are known to you, and you have a boulder or a rock which is sitting on top of it, and as a result of it, okay, how do you draw the forces, how do you resolve them, and how do you get an expression? That's what we have seen here. Okay, so far what we had been looking at is it's only about the objects that are at rest. Now what we will do is let us look at how to draw the free body diagrams when the objects are in motion, when the object is in motion, moving. Now towards it, the first kind of problem, okay, let me write it down. The free body diagrams, free bodies, FBDs, okay, when the object is in motion. When the object is in motion. This is what we are going to look into. Now towards it, now let me consider a horizontal table as usual. And I have an object. And I am pulling this object with a force. Let me assume that there is a friction here. So when I say there is a friction over here, so this has a friction. Now, let us understand how do I write the free body diagrams here. As usual, when the object is resting on a surface, the mg force will be acting downwards. The normal force would be acting upwards. This is clear. And then, since I said there is a friction here and the object is moving like this, the frictional force is acting here like this, right? Now there are 2 conditions that can arise. The first condition is that while you read the problem, if it says the object has been applied a force F and as a result of it, it is getting accelerated. If it says acceleration, you just say acceleration here. Okay, why in this direction? Why not this direction? Because the object is moving in this way. And acceleration is nothing but increase in the speed divided by time taken, or increase in velocity divided by time taken. So when I say increase in velocity, velocity is changing in this direction, right? As a result of this, you can put the acceleration here. Now, what is the end result of this? The first one is when you read a problem, you should be able to write the force body diagrams, free body diagrams. Okay. And the second one is after you write it, you should indicate the arrows and tell us, okay, where are the forces acting? What are the directions of these forces? And lastly, arrive at the consequence of these free body diagrams. What is the consequence? Writing the force equations. Now, how do I write the force equation? This is the question here. So towards it, we take up the y-axis here, and then I'll write this as n minus mg. Okay, let me write it in a different way now. Okay, I will write. See, the body is neither moving upwards nor downwards. Let me take up one of these direction. Let's say, for example, n minus mg is equal to m into a, but it's not moving anywhere. So I'll put this as 0. No acceleration along the y-axis. And thus I can now write n is equal to mg. This is my first equation. Right. Then the second equation. Now you see the object is moving like this over here. The forward force, okay, is taken along the direction of motion. Okay, if you ask me, why should I take up this force? Whichever direction the object is moving, okay, that force should be considered first. So the object is moving in this direction. So that force, F, is considered first. And then you see a force which is opposite to it is acting in this direction, which means F minus FF is acting in this direction. This should now be equal to the net force. The net force, according to Newton's second law, is given by m into a. Thus, I'll be able to write something like this. The force is equal to, okay, force minus FF, frictional force, is equal to m into a. Thus, we have got this. And we know that when the object is sliding, this should be written as FF. What is FF over here? FF is nothing but frictional force, which can be written as mu times n. So therefore, I'll write this as mu times n, mu times n. And what is normal force? See, from here, the normal force is mg, mu times mg. Okay, and thus I will write this as minus mu times mg is equal to m into a, or F should be equal to m into mu times g plus e, right? So what does it tell me? For example, if the value of mu is equal to some 0.3, for example, if I take mu equal to 0.3, then what will happen? Mu times g will become 3 over here. Now, you see here this a, okay, it's already moving at an acceleration. In addition to it, these 3 units are being added over here, right? So F is equal to, if I write this, m into a plus 3 over here, which means what? You should now apply a larger force over here. If there was no friction, you just apply a small force, the object will continue to move. But with the friction, what happens is you need to apply a larger force to see the same effect. That's what is being illustrated over here. Now, if I ask the question, what is the amount of force that I need to give? Okay, so that the object moves, then you can say the force that I need to give here is given by F equal to m into a plus 3, which means that I can still expand this, and I'll write this as 3 times F over here, which tells me that MA is nothing but F0. What is F0? F0 is nothing but, this is 3, I'm sorry, this is not 3F, this 3M. Okay, what is F0? F0 is nothing but the force that can be applied onto an object when there was no friction. F0 plus 3 times m. 3 times m means, okay, if the mass of the object is m over here, let us say 10 grams over here, then I should apply a force equal to 3 times m, which is 30. So I'll put this value equal to some 30 newtons over here. So whatever was the force that I had applied earlier, okay, without friction, I had to add 30 newtons to it so that the object starts moving. Is this clear? So why should you add? Because friction is pulling it. So you should overcome the friction, only then the object will move, right? Okay, now let us move on to the next one. So the second free body diagram. The second free body diagram tells me, let us say, for example, I have an object, okay, and this is being dropped. This is being dropped. Now, as it comes downwards, now you observe it is moving with an acceleration e. Okay, and then what is the force acting here? mg here. Okay, so now you need to write an equation for this. Is there a normal force here? There is no normal force over here. Why no normal force? because this is not resting on any surface here, right? So you cannot have a normal force. It's only mg over here. Okay, so which means the unbalanced force here is mg should now be equal to the net force acting on it, right? So this should now be equal to m into a. In other words, you can say that a is equal to g. Clear? Okay, the acceleration of the particle, okay, is equal to 9.8 meter per second square, which is nothing but an example of free fall, which we had seen in the first video. Okay, now what we do is, let me add some constraint here. So I have an object which is falling down, mg is the force acting here. Let us say, for example, I have put this into a tub of water or a bucket of water like this. Okay, now draw the free body diagram. If I want to draw the free body diagram here, now what can happen? See, as it falls down, see, if it was in air, there was no air resistance. It was also happily falling down. The moment it falls into water, the water molecules are now hating it. It dislikes it. And then because, you know, the cohesive force between the water molecules has been broken by this object. And as a result of this, it dislikes it and tries to oppose this and tries to oppose it like this. Okay, let the net force be FB. What do you call FB? As the force of buoyancy. See, I have written two arrows here. That doesn't indicate that I should write 2 FB here. Okay, so don't get confused. Sometimes even if I write so how many FBs over here, it doesn't mean that, okay, how many ever arrows I'm going to write, I'm going to use that value here. FB is a sum of all these arrows. Okay, so therefore, now how is the object moving? Object is moving this direction. What is the acceleration? Let me put this here. So what should I do here? Usually in physics, what we do, we consider anything that goes upwards as positive, anything that comes downwards is negative. Now here I'm not going to use that concept, but instead I will consider that mg is going downwards. Okay, so a is going down, not mg, the object is going downwards. So therefore this direction I will take it as positive. Now coming down direction is positive, and thus I will write the first force mg minus, if this is positive, the other direction should be negative, right? Any vector that you describe should be negative, minus FB should be equal to m into a. So have we arrived at one equation, right? Now do I have a normal force here? We do not have a normal force here, because you need to have a solid surface. Only then you will be able to have a normal force. Otherwise, you cannot put the normal force. Okay, so this is the force free body diagram, and this is the force equation for this. Now, let me take up a few more examples. Fourth one, let us say I have one object like this. I have a string connected to this. I have another object like this, and I apply this with a force F. Okay, now the question is, now let us say this has a mass m, this has a mass, let us say 2m. Okay, now if I have something like this, and let us say the friction here is F1. Okay, the friction here is F, the friction here is also seen to be F. Okay, so now the question is, draw the free body diagrams. See, in the earlier case, in question number 1, 2, 3, you had only one object. But here you observe there are two objects over here. Whenever we are drawing free body diagrams and you have two objects connected together, you should isolate one of them, solve it, and then you go to the second one. So towards it. Now, let me assume that this object is moving with an acceleration a. Now, what about this object? Will this also move with an acceleration a? Now, how do I know or not? Okay, let me explain it like this. Let us say I applied a force of some 20 Newton, and the next second, okay, this object is somewhere over here. This object would be somewhere over here. Now, do you think if the distance between these two, let us say initially is something like 5 centimeter, will this also be 5 centimeter or more than 5 centimeter or less than 5 centimeter? So you can see that it will exactly be equal to 5 centimeter. Why? Because the string is not extensible, right? The string has been connected. It's like a wire. It's a rigid wire. You will not be able to extend it. Of course, if you had connected this with a rubber band, then things would have changed, right? Okay, now let us come back to rubber band later on. Now, therefore, so with however this particle experiences a change in velocity over time, this will also experience the same change in velocity over time. Remember this. Okay, next, now we have, now let us take up one of these particles. Let us take up this one here. Okay. So I'll isolate only one of them. So I'll take one of them. This is the object, this is the surface. There's a frictional force acting here. Let us draw the free body diagram. Forget about everything else. There's a frictional force here. There's a normal force here. There's an mg force downwards. There's an applied force. Do you think I'm missing something? Or have I drawn everything? I'm missing something here. What is it? See, there's a string connected here, right? Now, what does a string do? If you connect any object to a string, the work of a string is only to pull it upwards, sidewards, wherever it is. So there is a force which is acting like this. So this is your tension force, right? So we have taken one object, we have drawn all the forces which are required here. And the object is also moving. Now let us write the force diagrams. First question. So what is your reference direction? The reference direction should be in the direction of motion of the particle, which means this should be your reference direction. That means any vector that you write here is positive, opposite direction is negative. So let me write down F minus T minus small f should be equal to ma, right? This is my first equation. Then now we have solved the equation for the x-axis. Let us look at for the y-axis. Along the y-axis, what happens? Is it bumping up and down? Is it going downwards, going upwards? No acceleration, no change in motion along the y-axis. So therefore, I can just write N is equal to mg. This is my second equation. We have one more equation also. What is that equation? Frictional force. This is sliding friction. Sliding friction will be written as mu times N, and here we see mu times mg, right? So therefore, it's mu times mg, and thus I can now substitute it over here, and thus I'll get this as F minus T minus mu times mg is equal to m into E, right? And then I will be able to solve it. Okay, so I have got one more equation here. Okay, I'll do one thing. I'll not write this equation. Okay, so now we have written two equations here. We have considered only one block here. We have considered only this block. We have considered only this block. I said that initially that when you are discussing free body diagrams for a system of two objects, then each block should be considered separately, and then you need to solve it. Okay, so we have got two equations here. Now let us take up the second block. Second block is here like this. There's a string connected to it. The block moves because the same tension is acting here. Tension is acting here. This force will not act here. This force only acts on these objects. Tension is acting there. Moving with an uniform acceleration. There is a frictional force. This is resting on the table. So mg is downwards. Normal force is upwards. Now we have taken care of all the parameters. Now what we will do is, let us write down the force equations. What are the force equations? T, see this is moving in this direction. So this direction should be positive. T minus frictional force should now be equal to, what is it? It's moving with the net force, ma, right? And then next one, let me call this as equation number 3. What's the next one? Next one tells you that N is equal to mg. And then this is 2m here. Oh my God, we should make it as 2m here. It should be 2mg here, right? And then we also have frictional force is equal to mu times N, which should be mu times 2mg. This is what is the frictional force. Okay. Now we have, I missed one equation number here. Let me call this as 3 here. And I should call this as F1 here and this is F2 here, because you see the masses are different. Okay, so this should be F1 here, this should be F2 here, right? Okay, let me 3, this is, okay, let me do one thing. Let me put this 5 here. Let me put this as 6 here. I don't want to change these numbers. Now we need to solve each and everything. Now how do we solve this? Now towards it, let us take up this example. From 3 and 6, what do we have here? T minus F2. What is F2? F2 is nothing but mu times 2mg is equal to 2ma. So T should be equal to 2m into mu g plus E. We have got one equation. Now what have we got? If I am able to measure the value of acceleration, then I can find out what is the tension, right? Just give me a moment. Okay, I'm back. Okay, so I am able to get the value of T is equal to 2m into mu g plus E. Now I can take this value of T, substitute it here to get the value of force, right? So I will now write F is equal to ma plus what is this F1 here? F1, as we know, F1 here is mu times mg plus T plus 2m into mu g plus 2ma. So what is the answer here? See, this is 2m mu g plus mu mg should be 3m mu g, and this is ma plus 2ma, which is 3ma. So this should be 3ma plus 3 mu mg. So we have got the total force. Now see, what all can we do? We will be able to find out what is the acceleration, what is the force acting on it, what is the tension on the string. I'll be able to do all this. Okay, I'm just showing you an example. There's no such questions being framed. I had just given an example. If the complexity increases from one object to the second object, then how do you resolve it? That's what we have done. Okay, now let us move on to the next type of problem. So what we have done is we have done one body problem. We have taken two objects and tried to create a free body diagram. And the two objects were, how were the two objects over here? See, the two objects were like this, okay, horizontally. Now let us take the two objects, same two objects, vertically, like this. I'll put one object here, mass m, put one other object here, mass 2m. Now what do you understand from here? Which direction will the object move? The object certainly moves downwards in this direction, because you see the mass is higher here, mass is lower over here. Now there's a string connected to this. Now this string, what is the work of a string? Pulls, right? The string only pulls the objects. So it pulls it like this. It pulls it like this over here, right? So most of the students make a mistake here while writing the direction, saying that if it is pulling like this, they should push it like this. Because if the string's work is to push, then what can happen is this mass will go down, right? So it is not happening. So as a result of it, understand, whenever I put one object and I put a string, the string always try to pull the object. Okay, so it's pulling the object. There's a pulley, and the string goes over the pulley and comes down like this. Now, the acceleration direction is shown over here. Now, what about the weight? Weight always acts downwards. This is 2mg downwards, mg downwards over here. Now, when the object is pulled like this object goes upwards like this, right? Now, let us understand. Okay, let us draw the free body diagram. Do I have a normal force here? I do not have a normal force because there is no surface where it is standing. So what did I say? When I want to draw a free body diagram, I should first take one of the objects, then analyze it, and then go to the second one. So let us take up the first mass, 2m. Now this is the string. This is the string. Tension is acting here. Is the tension different between these two edges? No. You see, the tension just goes around the same rope. So as a result of it, tension is same. Okay. And then one more thing which I need to highlight here is that I will say that this pulley is massless and sliding friction to be considered. Okay, which means this is not one more object that I should consider. The string is only between these two. This pulley is massless. Maybe something like this is 20 kg, this is 10 kg, and this is only 100 grams. Okay, so you can say the pulley is massless, right? Now, this is mass 2m. So 2mg is acting like this over here. And there is an acceleration which is falling down like this over here. So towards it, now what should I do? I should be able to write a force equation. Now, how do I write the force equation? What is the direction? First, reference direction is downwards over here because the object is moving downwards. So I will write this as 2mg minus t is equal to 2ma. Many of the students make a mistake here, writing this as m into a, because you see the mass is 2m here, not m. So I'm going to write like this. Then, do I have a friction here? I do not have a friction. Why? Because there is no surface over here, right? There's no surface. So as a result of it, I can just write like this over here. Now, let us consider the second object. I have only one equation to be written here. Let us consider second object. In the second object, now what happens once again? Now, second object, I will write it here. This is mass M. mg is acting downwards. T is acting upwards. And what about the acceleration? The mass is going upwards. Acceleration is upwards over here. So towards it, what is my reference direction? Reference direction is upwards, right? Because you see, so in this object, it is going upwards, but this object is coming downwards. So for the first mass, it is 2m mass. Okay, reference direction is downwards, which means anything that you consider downward is positive and opposite to it is negative. But here it is a different one. Now let us write down this also. T minus mg is equal to ma. Thus we have two equations. Let us solve them. So how do I solve them? Either I can take this value of t, substitute it here, or I can add 1 and 2 together. My easiest way to doing it. So when I do this, this tension and this tension will cancel. Let us do that also. So 2mg minus t plus tension minus mg should be equal to 2ma plus ma should be 3ma. These two gets cancels, and as a result of it, you get this as mg is equal to 3ma, or a should be equal to g by 3. What does this tell you? It tells you that the acceleration of the entire system here is seen to be 1/3 of g. Okay, then now let us find out the tension here. If I want to find the tension T is equal to mg plus ma. Now which should be mg plus m into g by 3. Why g by 3? I have taken this substituted over here. This should now be equal to 4mg by 3. Right? This should be 4mg by 3, which is nearly equal to 1.33 mg. Now you need to look at something here. If I have two objects connected by a single string like this, this is 2m, this m here stacked together, and you ask me what is the tension here. The tension here, if the object is at rest, this would be 3mg here. Okay, but while if you look at this point, you see the tension here is it to be 1.33 mg, right? Very, very lesser over here. Okay, the reason is because, so you observe that the object is also moving and it is being distributed equally, and as a result of it, the tension is lesser. Now I have a question here. Let us say I take a scissor and cut this part of the string. When I cut the part of the string, then what will happen? The object will start moving downwards over here, right? The object will start moving downwards over here. Now, what is the tension in the string? Can somebody tell me what is the tension in the string? The tension in the string. Now, let us draw the free body diagram. Okay, in the cut position. In the cut position, this is what is my mass, 2m here. 2mg will be acting downwards. Acceleration is acting like this. Now, what is tension? Tension is pulling force, right? This should be your tension here. But unfortunately, when you cut it across, there is no ceiling. So every part of the string is moving with the same acceleration, and there's no pulling force upwards over here, right? See, if there is a pulling force upwards, the object will not move downwards. But you see, every part of the string is now moving with the same acceleration as this moving, and as a result of it, the tension here is equal to 0. Okay, when the tension is 0, when you cut a string, the tension becomes 0, and then you observe that this now the free body diagram in this situation would now be equal to 2mg is equal to 2ma, or a should be equal to g. The particle now behaves like a free particle, right? What is free particle? What is free fall? Free fall is nothing but when there is no external force apart from the gravity, then that is what you call as free fall. Now you observe that there is a free fall being happening, right? Okay, so we have seen free body diagrams when the object is moving. Okay, we have seen 5 different examples. Anything else that I have missed it here? I don't think so. Okay, let me take up one more example also. 6th one. I have a spherical ball. Usually I take a rectangular one. I have taken a spherical ball like this. Draw the free body diagram for this. Okay, and get the forces. Now, the object is at rest. I have not made it to move. Now, what are the forces acting here? Normal force is acting upwards. mg force is acting downwards. It's at rest. So I can write this as N equal to mg, because it's not rolling, sliding, nothing is happening here, right? Let me take one more example also. I have a ladder that is resting between two walls. One the floor, other one is a vertical wall. Now, what is the free body diagram for this? Again, a static case. So in this case, now you see the ladder has a mass. The ladder has a mass. When I say the ladder has a mass, this is my ladder. Now, where will the mass be focused? The mass would be focused at the middle. This would be your mg. Okay, it's been kept slanting, but the mass will be acting at the middle part of the ladder. And then, see, this is resting over here. If it is resting over here, then see, actually, because of this mass, you should expect the ladder should fall down like this. It should move away like this. If it is not moving like this, so it means something is preventing here. Okay, maybe somebody is holding here. If nobody is holding, then the surface here is holding, which means what? There is a frictional force here. Let me write this as F1, right? There's a frictional force here. Then, what's the normal force? Normal force is acting here. N1 is acting here because it's touching the surface. So definitely N1 should be acting here. Now you see, mg and N1 are separated by a distance. If you had looked at an object, you had always written N1 and mg like this. They were together in a line. But here you see, there's a difference between these two. I tell you what is this difference leads to. Now, we have taken only one part of the surface because this is now, the ladder is now being, okay, clinging on to two surfaces. One is to this surface, the other one is this surface here, right? In this surface, you observe, once again, it is clinging over here. So this will now have a normal force like this. Now you see, I have a different normal force. The normal force is perpendicular to the surface, okay, not to the ladder. Do not write the normal force like this, which would be incorrect. Okay, you should write like this. This is my N2. And then, now once again, if you leave the ladder, let us say, because if there is no friction here, now this might be pulled downwards over here. But unfortunately, it is not being pulled downwards, and hence there is an opposing force here. So this is your frictional force. Thus you see N2, F2. So I have drawn all the forces over here. Okay, the next part is arriving at the force equations, right? The force equations now would be equal to N1 plus F2 is equal to mg. See, N1 plus F2 is equal to mg because it's at rest. The next one is N2. If this is forward direction, N2, this is opposite, minus F1. Is there any other force? No forces. So is equal to 0. This is my second equation. So simple, right? Okay. So this is the way how you can draw the free body diagrams for any kind of situation that has been given to you. I think we missed one more. Right. Let me do that also. 8th one. I have a table. I kept an object here. And then there's a pulley. From the end of the pulley, I put one more mass here. Let me say this mass is M. This mass is M1. This mass is M2. It's touching here. And there's a friction on the table. Frictional force is FF. Now you see. Now, when will the object come down? Let me assume, okay. Let me assume the acceleration is the object is falling down. Okay. For some reason, object is falling down. And as a result of this, now we have two objects. Whenever we have two objects, we should first take up only one of the object and draw the free body diagram. Which means I'm just going to take this one, M1. Take M1G is the force acting downwards. Tension is the force acting upwards over here. Which means there's a tensional force acting here. And then there's a tensional force acting here. See, if this rope is pulling the object upwards. This rope is pulling the object, okay, sideways, right? Okay, and now let us draw the free body diagram. This is my acceleration here. So for this correspondingly, so this direction is a positive direction. So I'll write this as M1G minus T is equal to M1G. Note that the object is not touching here. So I'm going to get like this. Now let us take up this one. Now for this one, the object is moving with an acceleration A. So this direction is positive. So I will write down once again. This is pulled by a tensional force like this. This is my acceleration. This is my frictional force. This is M2. And then this is my normal. This is my M2G. Remember, you have to write all the forces. Don't say that, okay, anyway, the object is not moving over here. I need not write it. Okay. So when you talk about a free body diagram, what are all forces acting over here? You should be able to write it. Right. And then next is, let us write on the force equation. The force equation. See, this side is positive. So I can write T minus FF should now be equal to M2 into E. And then we also know that N is equal to M2G. And since the box is sliding, I can now write frictional force is equal to mu times N, which should be mu times M2G. Now you substitute it over here. I get the answer as, okay, let us not substitute. Okay, let us just keep it like this. Now we have two equations. One equation here, second equation here, third equation here, fourth equation here. The purpose of drawing a free body diagram is to get the force equations. And once you get the force equations, you try to solve it to get an expression for tension, acceleration. This is what you need to do. So towards it, first try to get an expression for the acceleration. So towards it, what will I do? I will add up 1 and 2. Why should I add it up? Because the tension will get cancelled here, right? So M1G minus T plus T minus frictional force is equal to M1 plus M2 into E. This 2 goes away. Now I have frictional force. I'll write this as M1G minus frictional force. What is frictional force here? Mu times M2G is equal to M1 plus M2 into A. This implies M1 minus mu times M2 into G divided by M1 plus M2 is equal to A. So what is it we have got? We have got an expression for the acceleration of this system, right? And then if I want to find the tension, tension should now be equal to frictional force plus M2E from this equation. And thus I have frictional force is nothing but mu times M2G plus M2 into whatever we have got here. You can substitute it, then solve it to get a net expression for the tension. Okay, so with this, we'll stop here for the free body diagrams. So these are some of the examples. Okay, if you learn how to solve problems by practicing these problems, then definitely you'll be able to solve any kind of free body diagram problems. Okay, fine. Thank you, students, for watching. Like and subscribe to our channel to get more updates about the physics problems that we solve. Thank you.